Mr. T here with a definite integral application, and this time we're going to be looking at the area between two curves. In an earlier tutorial we have one where we have the area under a curve bounded by the x-axis and a left and right bound. In this case we're going to be looking at the area between two curves. We'll start out here with a fairly simple example, and we have these two functions and we're looking for the area that's bounded by those two curves. If we use the graphing calculator here, I've entered the functions and set an appropriate window so that we can look at the graph. And we have our f of x here, a linear function, and a parabola for g of x. So let's just make a quick sketch of this over here so we can talk about what it is that we are trying to accomplish here. So we have a parabola here and a line going through the parabola. So we are looking, what the problem's asking for is the bounded area is outlined here. So we are trying to find this area inside here. Let's talk about how we could go about doing that. Now we're going to need to know our left bound here and our right bound for doing our integration, and those will be the x points of the intersection. So let's use the calculator here to quickly find our intersection points. So we have an intersection point here at 1, 3, so this x value here is x equals 1. And let's find our second intersection. Is at 4, 6. Now we don't really care about the y values. We're at x equals 4. Now this parabola is our g of x, and this is our f of x. Now if we were going to try to do this maybe with graph paper or something, we could find the total area under this curve, and that would be the integral from 1 to 4 of g of x. And then we could subtract from it the area under our lower curve. So if we subtract that out, we're going to have the area we're looking for. And our lower curve is f of x. Now we have an integral property that could allow us, if we want to combine that into a single integral, or we could just integrate each of these separately and subtract the numbers. But if we want to try to do a single integral, then to find the area between two curves, we're going to have the integral between a and b of our upper function minus our lower function. Now when I'm working with the calculator, I don't always want to worry about which function is on top and which one's on the bottom, and sometimes I set up my calculator so that I can handle multiple problems quickly. To avoid this coming out to be a negative area, we can take a absolute value. Now if we were integrating by hand, taking the absolute integral of an absolute value function is more complicated, but with the graphing calculator it's no problem. So let's go to the graphing calculator and figure this out. We already have entered into y1 our f of x, and this is our g of x. So I'm going to calculate in y of 3, I'm going to calculate the difference of the two functions. Now we could retype in these functions, but we can use a capability on the calculator called vars, and we need y vars to get a function. So we're going to take function 1 minus function 2. Now again, if I was doing this properly, I might be worrying about which function is on top, in which case I really should be, to match what I have here, I should be taking y2 minus 1, y1. So I need to fix this either by changing that order, or as I said, I'm just going to fix this by inserting in here the absolute value function, and that way we will, since it's an area, we don't want a negative answer, we need a positive answer, so we can take this. If these functions, if one of these was a revenue, say these were revenue functions of two different models, and negative would tell us that one model is worse than the other, we could not take this technique here of the absolute value. But when we're dealing with areas, that can simplify for us. So now I need to integrate, but what I want to integrate is y3. So you need to be careful when you go to do our integrate function, number 7. Okay, we just graphed our difference, so we're going to be integrating under y3 under this difference function. But we want to make sure we're integrating the right function. So right by default, it's going to integrate y1. So I need to use these down arrow keys here to make sure y3 is listed up here. And now I can put in my lower limits, which for our problem was 1, and our upper limit is 4. And again, that's integrating our area here, but that area is the same area as this area in here. It's just been shifted down here. So we get 4.5. So the answer to our problem here is 4.5 square units. And again, that is the area between these two curves. So that's this area we found, but again on the graphing calculator down here, because this is our difference function. And again, we took absolute value of it to make sure no matter which of these two functions were on top that we have a positive area. Thank you. Hello, this is Mr. T with another area problem. Again, area between two curves. This time we have these two functions, f of x and g of x. I've entered them into the calculator here so we can take a look at what they look like. So our first function, f of x, is this cubic, and our g of x is this parabola. So if I make a little sketch over here, we have our cubic, and we have our parabola here. Not a very good parabola. Probably should have done those in two colors. This is our g of x. This is our f of x. And we're trying to find the area between the two curves, so we are trying to find these areas here, there, and this area here. Now from the last tutorial, one of our steps would be to find these intersection points. So here we have -2, -8. I did that earlier on my graphing calculator, just trying to save time here. This intersection is 0, 0, and this intersection is 2, 0. Now I'm going to work this problem first, making just a heads up so you don't write all this down. We're going to make a mistake here. So we're going to do this the incorrect way first. And we might have just remembered that to find the area between the two curves, that we take the area of the two functions, say f of x minus g of x, and we'll integrate them so we have the area going all the way from here to here. So let's integrate from -2 to +2. So we could use the calculator to do that. So my f of x is my y1 and my y2. So I go over here, and in y3 I'm going to use the vars function to put in f of x minus g of x. So function 1 minus function 2. And now I'm going to integrate my difference function here between -2 and 2. So again, we want to make sure we are integrating our y3, and we're going from -2 to 2. And our integral we get is essentially 0. Let's talk about why that happens. It's important that we understand what's going on here. On this part, our integral, the f of x is on top and g of x is on bottom. So when we do this definite integral for the interval between -2 and 0, we're going to get a positive number. In this interval, the functions flip order, so we have g of x on top and f of x. So when we subtract in this order, we've got the bottom function minus the top. This is going to come out with a negative definite integral. And in this particular issue, these two functions are the two halves of these lobes are symmetrical, so the two areas cancel each other out. If we had two areas where maybe this one was slightly bigger, we might do this calculation here and get a positive number and say, oh good, that's a positive number, I got this one right, whereas we may find out later, especially if it's a test, that we didn't get it correct. So let's talk about what we can do with this to properly get the answer. And there's kind of two approaches. There's kind of the formal approach that we would probably use in math in the textbook, and then we could talk about how a shortcut we can do with the graphing calculator. In your textbook, it's going to talk about breaking this up into two different area problems based on where these intersections are. So to find this first area on the left, we would integrate from -2 to 0, and in this range our f of x is on top, so we would integrate f of x minus g of x, and then we would add this area, and in that interval between 0 and 2, our g of x is the top function, so we need to subtract like this, and then we would have to evaluate each of these integrals and add the two results together. Since it's easy to integrate on the graphing calculator an absolute value function, we can combine these two into a single integral from -2 to 2, and we just need to make sure we take the absolute value of the difference. So we can fix that pretty easily on the mistake I made on the calculator. Let's go back to y1, and as we did in the first tutorial, let's take the absolute value of this difference. Well, let me go back to this graph. You can see here we've got one area that's above the x-axis, a positive area, and one axis below. So let's change our y1 here to, our y3 to put in the absolute value function. So let me insert math number absolute value. Let me close my parentheses here. And let's sketch the graph again. Let's pay attention to the third graph that comes up here. This is our difference one coming up. So notice now we've got the positive area here and a positive area. So when we integrate this y3, both these numbers are going to be positive and properly added together. So let's do our integration. Second calc 7. Again, as I highlighted, let's make sure we select the right function before we enter our limits. Now our limits go from -2 to 2, and we can hit enter. And we get the correct answer for this problem of an area of 24. If we did these separately, I'm not going to go through doing that, this area would come out to be 12, and this area, for this particular problem, again, those two parts are symmetrical, so we get 12 and 12. Up here, when we did the two parts, we got positive 12 for this one and negative 12 here. So I hope this helps, and this shortcut maybe can avoid making some mistakes, especially when you're allowed to use the graphing calculator. Hello, Mr. T here. We've got another area tutorial. The last two I did was the area between two curves. This one's worded a little differently, but we're going to see that it's very similar. We're going to find the area bounded by a curve and the x-axis. So we're looking for closed regions formed by our function and the x-axis. I've got a sample problem for us to look at here, a fairly simple one, but we just want to talk about the concepts here. Let's sketch a graph of this function. It's a cubic. Most of you would know the general shape of a cubic. And we can see here, let's just sketch a graph for us to talk about again. So we have a cubic function here. Now we could use the graphing calculator to find our x-intercepts because we are interested in the region said bounded by the x-axis and the function. So we're looking for those two areas. And so we want to find our x-intercepts here to find our bounds for our two regions. If we factored this, we could factor out a 3x and be left with x squared minus 4, giving us zeros of 0 and plus or minus 2. So this is negative 2, this is 0, and this is 2. Now we could treat this as area between two functions because the x-axis is the line y equals 0, or we could call it g of x equals 0. So just like in the last problem, we could set this up as the area, and we've got the two regions. Our first region goes from negative 2 to 0, and our f of x is on top, minus g of x, but g of x is 0, so we just get this. And then in the second interval, from 0 to 2, the x-axis is on top, so we've got 0 minus f of x, which would simplify to be negative f of x. Now we talked about a shortcut in the last tutorial that when some of the areas are below the x-axis and some above the x-axis, we can use our absolute value function to flip everything so that it's above the x-axis. So an alternative way of writing this would be to go from negative 2 to positive 2 of the absolute value of f of x. Now again, if we're integrating these by hand, sometimes doing the integral of an absolute value function, in fact, they have you split that up into separate parts. So this technique that I'm covering in this tutorial is highly tuned towards using our graphing calculator and using it effectively. So now we can change our function. So let's enter this, or let's actually just enter as f of 2 so that we can see the 2. Let's enter the absolute value of y1. So I'm going to use the math function to get to our absolute value. And again, we've been using today the vars function to bring up our other function, y1. So now we can graph. So we can see this second graph is flipping everything below the x-axis above. So we're going to be, when we integrate between negative 2 and 2, getting this area and this area. But this area is the same size as this area. So we're still getting the answer we need. So we can do our second calc to get to our integration, definite integral. And again, we want to make sure we're integrating the right one. We want the one that's the absolute value, and I put that into y2. And we're going from negative 2 to positive 2. And we integrate, and we get an area of 24. So again, just in summary, we can treat the integral bounded by a single function and the x-axis, just like we did in the last tutorial on area between two curves, because the x-axis is a function and it's the function y equals 0, or some f of x or g of x equals 0. I hope this helps, and talk to you on the flip side.